about to start. We'll talk about code or whatever we'll talk about today. It's about to start, so please hang tight while I check that everything is okay. Sound check, camera check, lights check. How's my hair? Oh, wait, I don't have any hair. Maybe put some pants on and I am good to go. So get ready wherever you are, 'cause this stream is about to start. Get ready wherever you are, 'cause this stream is about to start. Hi, my name is Leandro Facchinetti, and let's write some code together, shall we? What we have on the menu today is exactly and only what was on the title of the stream. We are going to develop a multi-channel circular buffer. Oh man, why am I doing this? You may be wondering. Well, it is because I want to have an effect, for example, just like this, that shows the waveform of the audio. In case you're new here, I'm doing real-time audio effects in REAPER, and I'm focusing on the visualization aspects of audio effects. I want to be able to show what the effect is doing to the audio. And in many cases, like compressors, it makes sense to show the waveform. And when there are two or more waveforms that are supposed to be in sync, they are supposed to scroll together, two issues occur. First, this one on the bottom is blinking, and I don't know what that's about. But the second issue is that the top and the bottom one, they scroll out of sync. Now, I'm not 100% sure that you can see this on the stream. You may not be able to because the resolution and the frame rate is smaller on YouTube. But the reason why they're scrolling out of sync, they're not completely out of sync, okay? They just jitter out of sync as they move across the screen. The reason why that is happening has to do with, oh boy, let me close this because it may be affecting the performance of this stream even. So the reason why that's happening, or at least I think the reason why that's happening, is that we have independent circular buffers for the top and bottom images, for the top and bottom waveforms. And when I say independent circular buffers, I mean that we use circular buffers for the audio thread to communicate with the user interface thread. The audio thread is pushing samples into the circular buffer as audio comes in. The user interface thread is reading samples out of that circular buffer. And each waveform has its own circular buffer, and the write heads may be advancing out of sync. That sort of thing may be happening. And I think that that's what's causing the desync or the little jittery effect. And there are good reasons to do multi-channel circular buffers, even if that was not the case. Because in many places where we use circular buffers, we end up having to do something like this, where we have one circular buffer per channel. That is something that makes sense when you're doing delays and you want to delay all the channels, or when you are doing the waveform thing where you want to have one waveform per channel, or even in the implementation of waveforms, we use circular buffers and we store the minimum and the maximum sample to do one slice of the waveform. That could also be a multi-channel circular buffer, and then the channels are not really left and right, the channels are top and bottom, minimum and maximum. And I mentioned before, and I think I mentioned this on Wednesday when I was doing a dramatic reading of the oscilloscope by Cocos. I mentioned that we did this before on the stream, way back. If you watch regularly, then you may remember that we had a multi-channel circular buffer at some point. I decided not to have it anymore because if you have a multi-channel circular buffer, why don't you have a multi-channel waveform display? Why don't you have multi-channel this and that and the other? But the truth is that the circular buffer may be special, or maybe even it may be worth it to do multi-channel everything. I don't know, we'll see. For now, we'll just focus on the idea of turning our circular buffers into a multi-channel thing. So this is the implementation of the circular buffer. It isn't huge. But we are going to revisit this. And I could have a multi-channel alternative to this, to the circular buffer, but I think I better maintain just one version. And I think that that might be the circular buffer, the multi-channel one. So I can already expect to have more fields here, perhaps. Let's think about this. So the current implementation is a data structure. It has two fields: the length of the circular buffer, and then the write index. The length is just how many elements there are in the circular buffer, and the write index is a pointer to the current location where we are writing to. Do we need to store the number of channels in the circular buffer? At first I thought we would need that, and that's why I started to write here a new line. But we may not. Hey Bo, I am well. I hope you're doing good too. Alrighty. So why would we need the number of channels here? Perhaps just for the user of the data structure to query the number of channels if they want to do some sort of looping. So I guess it can be handy to have that information here, but I don't think it's strictly necessary for the operation of the circular buffer itself. Hello, Dale. It's great to have you here. I hope you enjoy today's session. Alrighty, so let's add one field to the data structure. We have the length and the write index. I think that the number of channels will be the first. So channels will be -1, -2, -3. So we just added a field to the data structure, and the circular buffer is a bit of a clever data structure where I do negative indices. So when you allocate a circular buffer, when you allocate a circular buffer, you used to get a pointer in memory that you can just index into like this and get the second value in the circular buffer. That used to be the case, and to make this neat syntax work, I used the trick of putting extra data on the negative indices, and then I would offset the memory location to make that work. But now that we have multiple channels, this syntax just doesn't work because you want the second element from which channel. So we will need to have an extra function to get absolute positions. Right now, we have a get function given an offset from the write index, but we'll need to have two flavors of get. All right, so I guess I I will remember. I will remember. I will not take notes. So in that case, this data structure really just becomes a good old regular data structure where we store the number of channels in position 0, the length in position 1, the write index in position 2. Then to allocate a new buffer, you will need to give me the number of channels and a length. And then I will need to store 3 positions plus, so I don't need the offset anymore. Okay, so it's 3 positions for these 3 fields plus the length times the number of channels. Let's think about this for a moment. So if you have 2 channels, it's a stereo circular buffer. You have 2 channels and each circular buffer is 1,000 items. Then it will be 2 times 1,000. That will be the number of slots in memory that we need to allocate. Oh, and perhaps we also need a base address kind of thing. And this is not something that we need to allocate a space for. It will be just the location where this starts. Or perhaps I would just call these buffers. Good. Then to initialize the data structure, I am going to set the number of channels, the length, the write index, and buffers is just this position here. So that has already, or this position where I have the buffers here. So this bit I will not need to initialize in any way. Yeah, that's an unusual arrangement. And I guess to make this more regular, I could just have an address here, but then it would be really silly because in memory, a circular buffer would be the number of channels. So let's say 2 channels, then the length, let's say 1,000 samples, then the write index starting with 0, and then an address to the buffers. And then the address would be something like an address, but then the buffers would follow because I would need to allocate space for the buffers, and it would be guaranteed that the address of this position in memory is that one. So you are guaranteed to be pointing at the next position. So it's a bit of an unusual data structure in the sense that I don't initialize this field and I don't allocate memory for it explicitly, but it is the nature of the data structure. I think it will be fine to have this as an exception to the rule. Sure, it's going to be great. I really do enjoy watching you code. I really do enjoy you watching me code. Right, so when we are pushing a sample into the circular buffer or pushing a value into the circular buffer, we need to say at which channel we are doing that. So you give me the circular buffer, the channel, and the value. Should I pluralize this circular buffers? Perhaps. Because it's one circular buffer per channel. No, it's one circular buffer, and then there are channels in the circular buffer. It's a buffer with multiple channels. It's a multi-channel buffer. There you go. So I probably want to rename this, because these are not buffers. They are each one of the channels. I'll call these channels and these channels count. No. I'll call this base. Yeah, it's the base address of the circular buffer. There you go. Perhaps even base address. Yeah, base address. There you go. Now I like it. So to push a sample into the circular buffer, I will take the circular buffer, the channel, the and the value that I want to push. And I will need to fetch the length and the right index as well as the base address. No, the base address is not something that I store like that, so I don't need to get it. So just the length and the right index will be enough. So these two lines are okay. And then here I will need to compute what is the position. So it is this plus something plus right index. Let's get into this. So the circular buffer now has a base address. That's where you start each channel, the actual data that goes into the circular buffer. That's the position where it starts. So it is this base address plus the channel times the length. So this will get me to the right channel in that big chunk of memory. And you can see that this thing that I highlighted sort of resembles this thing, except that this is for all channels and this is for the current channel I'm interested in. And then into there, I will get my right index and I'll store my value in there. And it could be that you want to push samples into multiple channels before you advance the pointer. So the right index here, I will not really advance. So previously, when you push the sample into the circular buffer, because it was a single channel, it would advance the right index for you. Now you will have to push a sample and then advance the right index. And what would be a good name for this function? I guess next. Or perhaps advance. Yeah. And I just need the circular buffer for that. And it could be cute for me to return the right index. Not that it makes a huge difference. Okay. So now the API is you push a bunch of samples, probably on a loop. You push a bunch of samples into the circular buffer, then you advance the circular buffer when you're done. And if you forget to call this function, then you will have a bug. Oh, and I need this line here as well. So I fetch the right index, I advance it, I store the new one, and I return it just because I think it's cute to return it. Okay, so this is how you push samples into the circular buffer. How do you get samples from there? You will have two flavors, one which is absolute and the other which is relative. The absolute is given a position, and the relative is given an offset based on the right head. All right. Or perhaps I will call this the index, because I'm calling other things right index, read index. So I'll call this the index. All right. And what will I need? Well, it will be similar to this. Right. So I will need the length because I will need to wrap things around. I will need the right index. Not really. I will need, because this one is absolute, so it's not based on the right index, so I don't need it. The read index is also not necessary. I can just do that. And then I will have to do an arithmetic that is similar to this one that I used to write. Oh, and of course, if you are getting something, you better give me the number of the channel that you want to get from. All right, so circular buffer, go to the base address, add the channel, add the index, and that's your value. Great. Then to do it relative, let's see. Do I have any local variables on this one? I do. I have length. And on this one, I will need the write index. Then the read index needs to wrap. And that still makes sense. So I will have a line that reads pretty much like this, except that I will call this one the read index. And I think it makes sense to call this just index, because in this context, there is no write-read ambiguity. And on this context, there is a write and a read index, so they are called index, write index and read index. Just like that. Okay, so, oh, and then we have a flavor of getting that is interpolated. And this is an offset. So I might as well just have two flavors for absolute and relative that is interpolated. This is going to explode because anytime that I have another interpolation, like Lagrange interpolation, I will have to have an absolute and a relative version as well. So I could just extract the interpolation algorithm. But it can be handy to just get stuff from the circular buffer already interpolated. So I guess I will extract the interpolation functions, but then I will also have auxiliary functions that will use the absolute and relative indices. Yeah, all right, I'll bite the bullet. I will do that. But for now, I won't. So let's just forget about the interpolated version and see if the base implementation of just pushing things and getting things, if that much is working. All right, let's write a test for this. To create a circular buffer, we need to give the length as well as the number of channels. So I'll have a stereo with three positions. Then I will push into channels. I guess I will do everything in channel 0. So when you have two channels, they are labeled 0 and 1. And I will comment out the tests that have to do with the interpolated version. And this should work, because this amounts to the same test we had before. But there are other things in the library that depend on the circular buffer, and those tests may be failing now. So let's see other places in the library where we use circular buffers. So there is the waveform display, that's for sure. Oh, the waveform display is the only client of the circular buffer in the library. So as long as we don't use the waveform display, the test should be passing. Let's take a look. Where is the syntax error again? 726. Oh yeah, I renamed the function. Now it's called, this was the relative one. All right, yeah, let's do this. Oh, yeah, right. Okay, so this whole implementation is going to have syntax errors because even though I'm not running the waveform in my tests, I am still compiling. And the compiler checks the number of arguments passed to a function, which, by the way, is a cool feature. Anywho, circular counter, circular buffer fail. Oh, interesting. Okay. Who is failing? Okay, I have a circular buffer. Now let's put stuff in the circular buffer. Did that work? Oh, this guy is already failing. Why are you failing? Oh, because you evaluate to 0. Why do you evaluate to 0? Did you run? This evaluates to 1,000. That ran. This ran. This evaluates to a 0. What do we have in memory going on? So in position 0, what do we have in position 0? We have the number of channels. I expect to see 2 coming out of there. And I see. What do we have in position 1? The length. I expect to see the number 3 coming out of there. And we get it. Then the right index, well, that's more difficult. It's in position 2, so it's harder for me to predict, but it should be between 0 and 2. And it's 0. I'll take it. Oh, I forgot my own new API, didn't I? I said that if you forgot to call advanced, then you had an error. Well, I forgot, so I had an error. But now I don't have an error anymore. Take that. All right, reload, close, delete, re-add. I learned something about Reaper. If you're on this window for the effects for a track or an item or whatever, you can click on, you can type A and it opens this window. All right, the circular buffer tests are passing. Check this out. Let's commit what we have. And now let's add some more tests here because we are pushing into channel 0. Let's also use channel 1. And then let's also test stuff from channel 1. No, hang on, that's not what I want. That's what I want. And these are, they start with 2000. Alrighty. Am I missing anything? I don't think I am. The test should still be passing. And it is. Next. Am I missing tests for something? I am creating, I'm pushing, I'm advancing, I am getting. Oh, I am getting relative. Let's add tests for getting absolute. And the tests should even come first. Okay, let's reason about what should be in index 0. Well, I start at index 0 and then I push 1000. Index 1, oh, let's write this down then. And I guess this will be a good illustration of if you're not getting how I'm using memory. Now I think it will be clearer because there will be a visual indication of the layout of the memory of a circular buffer. So we have 2 channels and 3 places on each channel. So this is going to be channel 0 and channel 1. Then this, and let's have an indication that these are the channel. Then I will have the indices. And this is how the memory is organized. And that's why each of these slots is the size that is given. So 3 in this case, it has 3 elements. And that's why I multiply by length on the implementation when I get the base address. So a base address is just a pointer to here. And then yeah, let's get this little line here and go over how that works in case you are not really understand what's going on. Okay, so I have the base address. I start there. That's this part. Then I add channel. So for instance, if I'm interested in channel 1, it's 1 times the length. Remember that this is the length plus the write index. So if I am writing to index 1, for instance, I will get here and I will get this position in memory and I will write there. Cool. So let's have a values situation going on here and trace through this example. I start by pushing 1000 and 2000, and my write index is, let's put it here below. Well, except that it's also here. All right, that's my write index. And then let's put it there. So my values are 1000 and 2000. Then I advance. When I advance, I do this to the right pointer. And then the values are these guys. And then I advance again. And then the values are these guys. And then I advance again. And then I cannot go further, so I have to go back. And then the values are these guys. So that's what I expect to see in memory when this whole thing is over. Oh, actually, I I advance at the end, so I'm here. Remember that the write index points to the place where I'm about to write, not to the place that I have written to. And this is so that the offset plays out correctly. Great. So this is what I expect to see in memory at the end of this whole block. And then let's go over get absolute channel 0, index 0. This is the value I expect. Channel 1, index 0, I expect 2030. And then duplicate. And this is going to be position 1 and position 2. Position 1, position 2. And I expect to see in position 1, 1010, 2010. And in position 2, which is this part, I expect to see 1020, 2020. All right. Now let's put me to the test. Did I work this out correctly? And I did. Yay me. Yeah, I don't think there is anything else here to do. Well, let's check that we have tested everything. We have. So now we have to deal with interpolation. Let's go ahead and do that. Or maybe not, because we don't need it for the waveform display. So perhaps let's adapt the waveform display to use this new circular buffer with multiple channels. Because that will prove that we have done the right move with this, with the subject of today's stream of the circular buffer with multiple channels. In fact, I have already accomplished the title of the stream, and that's rare that I do it and that I do it so fast. But yeah, we have multi-channel circular buffers already. So I guess I can postpone this. I'll just leave that to do here. And let's go back to the waveform display. I will have to restructure the waveform display quite a bit, because now the waveform display will also need to have some notion of multi-channel, and the way that that's going to play out can be tricky. So perhaps I can take this opportunity to sort of re-implement the waveform display, but I will be copying and pasting a lot, so it's not a from scratch situation. Let's revisit this, for instance. Will I need all of that? Perhaps not. For instance, these are circular buffers. Not that. These two are circular buffers. Now they can be a single thing. And before we even go into the nitty-gritty, let's think about how we want to go about this, because we learned stuff from the Caucus oscilloscope implementation. For one thing, it seems like perhaps bleeding is more expensive than redrawing. So we did a lot of work to have an off-screen image and bleed it and then erase it and then keep the transparency, keep the alpha. That was a lot of fun to write. We learned a lot about how off-screen drawing works, but it seems like that may be the reason for the blinking that we saw on the effect, because it has to bleed, and perhaps bleeding is expensive. Perhaps it's even more expensive than calling the drawing primitives in a loop. So let's think about what we want to do with the waveform display on a high level. We want to sync multiple waveforms, sync the scrolling of multiple waveforms. We want to use redrawing instead of bleeding. Because of what we learned from Caucus oscilloscope. And then there is also the question of who does the work of taking samples and computing the maximum and the minimum. In the oscilloscope, the job was done in the UI thread. But I think it is advantageous to do it on the sample thread, on the audio thread. They had to do it on the UI thread because you may be able to zoom and get down to a single sample if needed. We don't have that need, I don't think. So, in fact, to back this decision, let's do some quick computation. Suppose that I am using my waveform display to do my auto mixer. So I want to show one waveform. What the heck? Let's say that everyone is using a stereo microphone. Worst case scenario. Everyone is using a stereo microphone. And let's say that we have 20 people. It's a lot of waveforms. And let's say that it makes sense for the auto mixer to show 5 seconds worth of audio. Now the question is, and let's suppose that you are using a reasonable sample rate of 48 kilohertz or 48,000 hertz, like this. So now the question becomes, how many samples do we need to store to make this display happen? So that's 2 channels per mic. So 2 channels per microphone with 20 microphones, that's 40 channels total. And 5 seconds at 48,000 hertz is 2400,000 samples per channel. And that is more than 8 million. So we would be using more memory than JSFX lets us use. Yeah, and you would be storing this for almost no good reason. So yeah, the approach used by the oscilloscope is not only overkill, it is not really manageable. Because we can ask for more memory. We can ask JSFX to give us 16,000 or 16 million, I think, is the upper limit of how much we can ask. But for this purpose, it really is overkill. So the approach used by the oscilloscope will not fly. We cannot just store all the samples. Now we have 2 options. We can store some samples, like we did at one point. We implemented this waveform in so many ways. So at one point we had the audio thread writing just enough samples. It was a relatively small circular buffer, just enough samples for the user interface thread to come in and consume them. And I guess that is okay. So yeah, we do have the option of doing the bulk of the work of taking many, many samples and deciding how to draw them. We can do this work on the audio thread. We can do this work on the user interface thread. If we did it on the user interface thread, we could try to get away with not turning off the collection of samples. Let me explain what I mean. In the oscilloscope, they are always pushing samples into the circular buffer, unless you explicitly hold. But other than that, even if the effect is closed and the user interface is not showing, you're still doing this work. We, on the other hand, we have a way of knowing we have a way of knowing if the user interface is showing, and we only do the work of pushing if the user interface is showing. But if we decide to just push some samples, just enough samples, not the full stuff, I mean, the buffers would not have this length. Let's say that the buffers would be half a second or perhaps even shorter than that. We could just have a buffer of half a second, and this guy could be consuming that. But if the user interface is closed, this guy would not be consuming that. And this guy would just keep pushing samples just like this one does. It could be okay. And it would alleviate the need to actually detect if the user interface is open and whatnot. But now we already have that infrastructure, and I'm tempted to use it because I think it makes sense to do the decimation on the audio thread. Yeah, so that's what we have been doing on this implementation that is here. So that's what we are going to continue to do. So do the decimation on the audio thread. And when I say decimation, I mean this loop that looks at all the samples and takes the minimum and the maximum and positions it on the screen and whatnot. All this work of determining from, like, let's say 1,000 samples is going to make up 1 pixel on the screen. All this work of taking 1,000 samples and producing 1 pixel, 1 column, is the decimation. Any other decisions that we need to make? Well, we need to change the way that we store, so we are not withdrawing. Sorry, we are not bleeding. So we will need to store this in some other way. Perhaps just on a circular buffer. Yeah, I think that will do. Yeah, I think I have a clear picture of how this is going to work. On the audio thread, we are going to do the decimation, and we are going to push into a circular buffer that will be big enough to show stuff on the screen. So the circular buffer will be like 8,000, thinking of the case where your screen is an 8K display. And then there will be a single circular buffer used to communicate between the audio thread and the UI thread, as well as used by the UI thread to do the drawing. And we had a problem with this in the past where there was a race condition that would like glitch the visualization on one of the sides. And my solution for that is just going to be to ignore a chunk of the circular buffer where the noise is supposed to be happening. And that implementation is more straightforward. It's closer to this one, the oscilloscope by Caucus. So I think I have a clear view, and I think that we implemented this circular buffer with multiple channels correctly. So I think that was not a lot of work, but it was honest work. We have a clear view. I'm not going to start diving into this because it's going to be a whole thing. I might just do it on the weekend because we all know what it looks like. But on the other hand, I don't know if I will have the time to do it on the weekend. So something will happen on Monday. I will be back and maybe I will have done this. Maybe I will be doing this. I don't know. There is still, I guess there is one thing that we still need to think about. And that's how we are going to use the circular buffers we have just implemented, the multi-channel circular buffers, how we are going to use that on the waveform display. I have two notions that could work. One is to have an API for the waveforms display that is pretty much the same as the API we have for the circular buffers, where you would push samples into multiple waveforms for multiple channels. And then advance. So you would push samples into circular buffers on different channels and then advance. And the second option would be to have a circular buffer that is external to the waveform display, and then you provide the circular buffer to the waveform display drawing mechanism. But then it requires you to handle this circular buffer as an external dependency. Yeah, that's no good. So we are going to just have the notion of multiple channels on the waveform display. Sync the scrolling of multiple waveforms by introducing multi-channel waveform display. Yeah, so I guess it's starting, the snowball effect is starting because I have multi-channel circular buffer. Now I will have multi-channel waveforms, and it will be cascading like that. It is what it is. The waveform is in essence a glorified circular buffer where there is more intelligence to the pushing. We are not just storing the samples, we are also doing this decimation along the way. So kind of stands to reason that multiple channels on the circular buffer entails multiple channels on the waveform implementation as well. And if you are doing something that is mono, then you will just have to cope with having to pass a bunch of zeros as the channel number. Perhaps I could even have an overload with the default parameter, but I don't think I will. So with that, it's time to say have a good weekend because it's Friday. Let's take it easy. Let's end the stream here since I don't want to dive into this. That's going to be complicated. Thank you, Bo and Theo, for being here with me today. Thank you everyone else who is watching, perhaps in the future. Just not active on the chat, but watching anyway. I appreciate you being here. And I see you on Monday for some more of this, perhaps. Have a good weekend. Bye. Thank you for watching the stream. You know how great it has been. Or maybe it sucked, and I am glad that you stuck with me. And soon we'll all be back together for some more coding or talking or chilling. The next time I'll be streaming.